Hello, Chemistry 2341. We're going to continue with Chapter 6, and this is Part 2, Ionic Reactions, specifically substitution. Let's first talk about the polar bond between the carbon and a halogen. Okay, the halogen is electronegative and therefore pulls electron density away from the carbon, making that carbon electron deficient. Now, what it also does is the size of the halogen also increases the length of the bond as you get to a larger and larger size. Notice the bond length between the carbon fluorine is shorter than carbon chlorine, which is shorter than the carbon bromine and the iodine. And this also decreases the bond strength as we increase that length of that bond. Those decreases in bond strength actually help us decide how things are going to trend in our substitution reactions. Okay, so in substitution reactions, we typically react a nucleophile with a substrate. It's important that the substrate have some type of leaving group, and so we have to distinguish the leaving group abilities as far as how it interacts with the nucleophile. Once the nucleophile comes in and attacks the substrate and the leaving group leaves, we end up with our new product, which has the nucleophilic attached to our organic compound, plus a leaving group, typically leaving as an anion. So things we have to consider are the ability for that leaving group to leave, the type and strength of the nucleophile we're using. There are also solvent effects associated with this, and then effects of the substrate, for example, how sterically demanding that substrate is. So not all nucleophiles actually have to have a full negative charge, but they all have a lone pair of electrons that can come in and create the new bond between the nucleophile and the substrate. And the electrons that were in the substrate and leaving group leave with the leaving group, typically creating an anion or a neutral molecule. So in the case of the first reaction here, we have the lone pair from the amine group coming in to attack the carbon and with having iodine leave as a negative charge. We can also have classical nucleophiles that actually have a full negative charge on them, like the hydroxide and the methoxide come in and attack our substrate, creating a new carbon-oxygen bond in both of those substrates. We can also have halogens come in and act as nucleophiles and displace other leaving groups, in this case, displacing another halogen. So let's talk a little bit about the leaving groups. In a nucleophilic substitution reaction, the bond between the carbon and whatever the leaving group has to be cleaved heterolytically, meaning that the electrons between the carbon and the leaving group leave with the leaving group, forming an anion or a neutral molecule. The more stable that leaving group is, the better able it is to accept that electron pair. So if it's leaving as a stable anion or as a neutral molecule, it makes it a better leaving group. Okay, so when we're comparing two leaving groups, the better leaving group is the one that is the weaker base. So if we think about our conjugate acids and look at our conjugate acid scale, the weaker base is always the better leaving group. So when we're comparing nucleophiles, we can look at that base strength. Okay? For example, water is a better leaving group than a hydroxide because water is the weaker base. Okay? Right now we're going to focus on halogens as leaving groups, but other groups can be used, and so we'll look at those as neutral leaving groups or other leaving groups. Okay, so there's trends in the leaving group ability. First of all, the weaker the base, the better the leaving group. So if we look just across the row of the periodic table, basicity decreases, so the leaving group ability increases, meaning that water is a better leaving group than ammonia because it is the weaker of the two bases. If we look at the halogens, it's the same trend where our basicity increases as we move up the periodic table to the smaller anion, and therefore our ability to leave increases with the going down the periodic table, where fluorine is not as good as chlorine, but bromine is better than chlorine, and iodine is better than bromine, making iodine one of the weakest bases and one of the best leaving groups out of the halogens. Okay, so when we have a nucleophile come and attack, that ability of those electrons between the carbon and the halide, or the carbon and the leaving group, to leave with that is the effect we're looking for here, the effect of the leaving group ability. Okay, so in general trends, the lower the pK of the conjugate acid, the weaker the base. So if we think about our strong acids like HI, HBr, and HCl, that makes them good leaving groups because all of their pKa's are below 0. That takes us to water as a really good leaving group because the hydronium ion has a pKa also less than 0. All right, now here's where we kind of switch over to the poorer leaving groups. If you think of fluoride ion, well, HF is not a strong acid. It does not completely dissociate in water, so its pKa is above 0, making it a weaker base than the other systems. And then as we move up to hydroxide ion, hydrogen as a negative charge, the amide ion, or even a carbon or carbanion, those are all very poor leaving groups. So when we're looking at these substitution reactions, if we're attacking any of these with fluoride ion, hydroxide ion, amide, or carbon anion, those are going to displace the better leaving groups like iodine, bromine, chlorine, and water. Okay, so let's do some examples of nucleophiles here. The most typical one we're going to see is negatively charged nucleophiles, and they yield neutral substitution products. The reason they do is that the electrons between the electron forming the anion is the one that attacks and creates the new bond with carbon, leaving a neutral substrate, and the negative charge leaves with the leaving group as in there. So good examples of this are hydroxide, thiolate, amide ion. When we deprotonate acetylene, the acetylene ion, alkoxy groups, which are alcohols that have had the hydrogen removed and a charge there, the acetate group, the cyanide group, or the nitrile group. Typically there's a metal counter ion, and this is just to balance charge and help dissolve them. What we use as the counter ion is typically left out of the equation just because it's a sodium ion on both sides, so we typically leave that out as a spectator ion. We can also attack with neutral nucleophiles like alcohols, water, ethers, amines, and ammonia. When we have those, we typically end up with a charged species. It has a positive G charge species, and then it has to interact with a base to make it back into a neutral species. So in the case here before, step 1 is our actual nucleophilic substitution, giving us our charged species here, and then typically a proton is transferred to some base in the reaction mixture, leading to our neutral product. Okay, these are some common nucleophiles. Oxygen has both hydroxide, the alkoxide, and the salts of carboxylic acids, in this case the acetate ion. Nitrogen, we have the amide ion here. The azide ion here, it's N3 minus. We can also have carbon as a nucleophile, like in the cyanide ion or the acetylide ion. Halogens like chlorine, bromine, and iodine can be used, and sulfur can be used if it's deprotonated once. We also have neutral nucleophiles like water and alcohols, ammonia and amines, and dihydrogen sulfide and thiolates. Okay. Typically, nucleophilicity does parallel basicity. Okay. For example, negatively charged nucleophile is always a stronger nucleophile than its conjugate acid. So hydroxide is the stronger base and therefore is a stronger nucleophile than water. Okay? If two nucleophiles have the same nucleophilic atom, i.e. oxygen, the stronger base is always the stronger nucleophile. So if we compare hydroxide to the alkoxide group here, hydroxide to the acetate group here, if we look at the relative pKa's of water and acetic acid, we can see that acetic acid is stronger. Therefore, the acetate ion is the weaker base, making hydroxide the stronger base, making hydroxide the stronger nucleophile. Okay. As we move across the periodic table from right to left, nucleophilicity increases as basicity increases. So when we have fluorine moving to oxygen, moving to nitrogen, moving to carbon, we have increasing nucleophilicity. So if we have an anion on carbon, we have a very strong nucleophile. So in the Okay, now there are some steric effects associated with nucleophilicity. nucleophilicity will not parallel basicity if it becomes sterically hindered. Sterically hindered means that there is a decrease in reactivity resulting from the presence of a bulky group at the site of the reaction. If you can imagine, it now is very difficult for that to come in and actually act as a nucleophile. It will start to decrease its nucleophilicity, but not its basicity, meaning that hindered bases like this T-butoxide here makes it a much stronger nucleophile, much stronger base than a nucleophile, because it's so big and bulky it can't come in and actually do the nucleophilic attack, but it can act as a base. If we look at something with a smaller group on the oxygen here, like ethyl, the ethyl group, it becomes a stronger nucleophile, but it is still a good base, but it is now more likely to act as a nucleophile, where the T-butoxide is more likely to act as a base. And this will become important as we move into the comparison between substitution reactions and elimination reactions. Okay, there's also an effect with solvent on nucleophilicity. So since we have to have the solvent actually dissolve polar materials, we typically use polar solvents to dissolve them. And we have two types of polar solvents that we're going to use. The first one is what we call a protic solvent. This is a solvent that can hydrogen bond. And it can hydrogen bond, so it solvates the cations and anions by being able to donate either the electron pair of the electron negative atom or the hydrogen from the protic portion or the hydrogen portion of it. So think, if it hydrogen bonds, it's a protic solvent. In contrast, we can also have these polar solvents that all have dipoles and all have strong dipole interactions, but they don't have a hydrogen that can hydrogen bond. That means these materials only solvate cations, and if it only solvates cations, that's going to affect the negative charge around our nucleophile. Okay, so if we think about it, in a protic solvent, like the one here on the left, we have water solubilizing the bromide ion. And it's hydrogen bonding, it's partially bonded to all those different hydrogens that are completely surrounded. Because it's partially bonded to all those around there through these partial hydrogen bonds, it is less nucleophilic. Its charge is spread out, it is partially bonded to all those partially positive sites, and therefore it loses its ionic strength, i.e. nucleophilicity. In polar aprotic solvents, the anion cannot share as much electron density. These are just dipole ion interactions as opposed to hydrogen bond ion interactions, and therefore they become more nucleophilic. This is very pronounced, especially in the halide series. Okay, so let's take a look at all the trends in solvent effects on nucleophilicity. The smaller, more electronegative anions are solvated more strongly, effectively shielding them from the reaction. Okay? Meaning that fluorine's the smallest, iodine's the biggest. So as we have increasing size, we have decreasing basicity. As we have that increasing size, we have increasing philicity in protic solvents. Okay, but the opposite is true for smaller ions. Okay, so nucleophilicity increases as we go down the column in polar protic solvents because the ion size increases. That is the opposite of the basicity. The nucleophilicity in polar protic solvents is the phthalate's higher than iodine, which is higher than hydroxide, which is higher than bromine, higher than chlorine, and water is the least nucleophilic in these polar protic solvents. Okay? In contrast, in the polar aprotic solvents, the nucleophilicity does parallel basicity, meaning that as the size goes down, the nucleophilicity goes up. So the halide nucleophilicity in polar solvents is completely backwards of the nucleophilicity in polar protic solvents. So fluoride becomes the better nucleophile, and it can displace iodine, which is completely opposite from the polar protic solvents above.